Hey everyone, welcome back to my channel. I hope you are loading awesome. So welcome back to another exciting video. So in this video, you already got from the thumbnail or title. So yeah, in this video we are just understanding the Java memory management. So for this, what I have done, I have drafted one article. So here all the key terms are there. So we'll understand all these things. I'll use or annotate few things where I think I should explain these, so else and also I'll attach the link of this article in the description, so you can go at the end, you can go and check it out and keep it as your reference as well. Okay, so understanding Java memory management, a complete guide. So yeah, this is the article. Okay, so let's start. So ever wondered how Java handles memory behind the scenes? Yeah, I did wonder because जब मुझे नहीं पता था तो I was also wondering कैसे करता है. Okay, might be you also now. As a Java developer, understanding memory management is crucial for writing efficient, scalable applications. In this comprehensive guide, we will dive deep into how the JVM manages memory, explore different memory areas, and learn about garbage collection strategies that keep your application running smoothly. Yes, exactly. Because if you know how your memory is being used by your application, so then you can improve the performance. How performance? Because if your application contains the memory leaks, you are opening the connection, you are not closing the connection, you are creating the memory, you are nested creating multiple references to your memory, and those are not freed up on time, then you will get out of memory, your application will become slow, it will take time. Okay, so how these all stuff handled inside your Java, so let's understand that. Okay, and one more thing, this is the video where we are understanding with context of Java, but I have one more video in the pipeline where we'll compare how C# garbage collector is different from your Java. So probably the next video will be on that. That is also in the pipeline. So as of now, let's start with this video. Okay, so what is memory management in Java? So memory management in Java is automatically handled by the JVM. If you don't know what is JVM, I already created one video where I showed you compiler versus JVM, so you can go and check it out there. Okay, so unlike languages like C or C++, you don't need to manually allocate or deallocate memory. The JVM takes care of this through sophisticated algorithms and processes, primarily using two main memory areas like stack and heap. Yeah, so basically inside your Java, memory management is automatically happen with the help of JVM. So you remember when I believe you worked on C or C++, where we have to manually create or I would say allocate or deallocate the memory using your malloc and calloc. Inside C we use malloc to create the memory, we define the size, and if you want to free up the memory, then we use free keyboard, and inside C++ we use delete. So yeah, but yeah, it has been so long since I worked on these C or C++ language, so I'm not exactly remember the keywords was what was to allocate or deallocate, but now I'm working on C# and Java, so it's automatically in Java it is handled by your JVM, and in C# it is handled by your CLR. Okay, so yeah, so here it says primarily using two main memory areas, stack and heap. Yes, absolutely. Inside your memory management we have two memories, one is your stack and another one is your heap, and these both are resides in your system's RAM. Okay, so both memory areas are created when the JVM starts and are stored in your system's RAM. Let's explore each one in detail. Cool. Okay, so stack memory, the fast lane. Okay, so what gets stored in stack memory? So inside the stack memory it stored your primitive data types like your int, double, char, etc. Okay, as you can see here, in double, boolean, char, etc. And your method specific variables and the parameters we have, or reference to objects, not the objects themselves, those live in the heap. So but does it mean references to objects, not the object themselves? Your noise are you tip tip tip, what is that? Isn't that annoying? I'll fix this in the morning. Okay, so let me help you with this, like reference to objects, not the object themselves. Just give a sec, I'm setting up the screen. Okay, so reference to object. So suppose like here we have one memory called your stack, and here the messy one, suppose we have heap. Okay, so now inside stack, suppose we have one class called your user, and now I am creating the object or the instance of your user, new user. Okay, so like it says reference to objects. So suppose this is my u, and here I have the object of user, which is u. Now this is referencing here. So stack stores the reference, not the object. So this is saying references to objects, not the object themselves, those live in the heap. Cool. Which means this u we are storing inside your stack, but actual memory object themselves, it reside in your heap. Okay, so next we have key characteristics. So thread local memory. So basically each thread has its own on stack, or I would say the local memory. So each thread gets its own stack memory space. This means variable in one thread stack are completely isolated from other threads stack. So suppose, what does this mean? So suppose if this is my one thread t1 and this is my thread t2, this will have their own stack and this thread will have their own stack, and the what variable we are using here, this will not be like your t2 will not know like what variable we are using inside t1, because they both have their own local stack and these variables will be isolated from each other. Threads are completely isolated from another thread stack. Cool. So LIFO order. Okay, so like stack memory follows strict order. The last variable added is the first one removed when it goes out of scope. So yeah, exactly. So like how it happens. So do we have example? Yeah. So suppose we have this example where we have your main. So how it's going? So suppose this is my stack memory. So when suppose our main method is called, so one scope is defined, so you can understand like this is the scope of your main. Okay, inside that you have int x is equal to 10, so your x will this is x, your x will reside here. Then you have string name Java, so you know name, only the name reference will be here, but your object will. So if you'll observe here, this is your heap, but here this string is a literal, and you already know that literals are stored inside your string pool. Where? Inside your string pool. If you don't know string pool, then you can just do Google, or okay, let me tell you. So suppose when I'm creating any literal, string s1 is equal to Java. Okay, and if I am doing string s2 equal to again Java. Cool. So what it will do, first it will, so suppose this is my, I'm writing sp, this is my string pool. So it will just store your literal here and the reference will be here. So when it will do string s2, first before creating the object or the memory for the s2, it will check first inside your string pool. If like Java is already there, it just reuse this one s, it will return the s1 address, it will not create the new one. But what if I'm using string s3 is equal to new string, and if here I'm parsing Java, so yeah, but in this case this will create new memory because it will not check in your string pool, but like for the literal it will check in the string pool if that is already there, so it will not create the another one. So okay, let's get back to our example. So here name will go inside your string pool, so we have the string pool. So next we have the display. So here we like one more scope for your display method, and here we are calling the, this has like your display created a new stack frame, new block, method call creates new stack frame. Then here we'll have your number, we'll have your text, and like here the scope is like ending, so we'll remove your this one and we'll remove your this one, and your like this scope is ended. Same way your this stack will get empty and all the reference will be removed by your GC. Okay, but how these reference will be removed, that we'll see later in the video, because there are like types of object references, I would say. Okay, so let's understand this here, we'll see later in the video what are those. Okay, so we were talking about LIFO, like stack memory follows strict order. Okay, so lightning fast access like memory allocation and deallocation in stack is extremely efficient due to simple structure. Yeah, we are just using the simple we are creating referencing and out, and inside stack we are just storing your primitive types and variable parameters and your just references. Cool, and this works in LIFO order. Cool. So limited size, stack memory has a fixed size limit, exceed it you will get a stack overflow error. Hello infinite recursion. Woo! So like what does it mean? So suppose you have one method called public void hello infinite, and inside that again you are calling hello infinite. Cool. So here you will get your stack overflow error because you are calling this method again and again, but there is no like break condition, like the exit criteria where we have to stop. Okay, that is required. So this stack memory in action, we have seen this example here, and next we have understanding the object references. So yeah, this is important. So not all references are created equal. Java has different type of references. The one is strong references, which is default one. Yeah, and then we have soft, then we have weak. Okay, so let's start with the strong and weak, then we'll see the soft. Okay, so as you, okay, let me again create here. So suppose this is my stack, just understand we have one user and this is my heap and this is your user's memory and there is you. Okay, you are it, where's the result? Oh no, this is you. Okay, so when we create instance object, reference stores here like variable and reference to the original memory inside your heap. So by default this is called your strong reference. So what happened when your GC runs, when your JVM like call or run your garbage collector, so it does not remove. So as you can see here, I have just expressed with the help of example, I want to be garbage collected. Your GC will not remove this reference because it's a strong reference. Then come your weak reference. So weak reference means, you can understand, you have another u2 and user object, and that could be like person or anything. Now here you have weak reference. You can see that partial arrow. This is your weak reference. So what happened here? So when your GC will run, gc.run, what it will do, it will check if there would be any weak reference. It will remove those reference and it will clean up the memory, freed up the space for you. Okay, so as you can see here, I can be collected anytime. Then we have one soft reference. By default strong reference, but for weak reference we have weak reference like class. With that we can create weak reference, and this will be whenever your GC will run, it will be collected or you will get the free memory. And next we have the soft one. Soft is your similar to weak reference, but it will only like removed by your GC when there is a memory required. Or you can see it is written here, I might be collected under memory pressure. When your JVM needs more memory to run anything, and if it sees like we have one like soft reference, so it can, if it requires more memory, it will just remove this reference and freed up the space, just took that space to go with the process. So these are the your type of references. One is your phantom reference, like post finalization cleanup, used for cleanup operations after an object has been finalized. Okay. Pro tip: calling system.gc request garbage collection but doesn't guarantee it will run immediately. The JVM decides when it's the right time to call or free up the memory. Okay, it is not recommended, or because it doesn't guarantee like whether it will run immediately or later. It all depends on like JVM. JVM will decide when to run and what is the right time to run this or call this. Okay, so that was all about our heap memory. Okay, so we have seen this was all about your heap memory. Cool. So next we have all about your stack memory. My bad. So now we'll start with the heap memory. So where objects live, as we saw here, so inside heap, here our objects live. Cool. So if stack memory is short-term memory, then heap memory is your application's long-term storage. This is where all objects and class level data reside. Yes, this is your long-term memory. So key features of heap memory, like shared among all threads. Yeah, all threads share the same heap memory. Unlike stack memory, heap memory is shared across all threads in our application. Automatic garbage collection, like the JVM automatically removes unreferenced objects through garbage collection processes. Dynamic size, heap memory can grow and shrink during runtime with JVM limits. Noise. So now yeah, this is like the diving deep into your heap. So the anatomy of heap memory. So young generation. So okay, so like inside your heap memory we have two generations. The one we can say your young generation, the one we can say your old generation. And then we have string pool. We already know string pool is inside your heap. And then we have meta space. So these three things we can say. We have string pool, and here we have meta space. Okay, so let's understand this. So inside young generation, so let me, ये क्या लिख दिया, मुझे अपनी हैंड राइटिंग थोड़ी सी सही कर लेनी चाहिए. I believe it's visible now and readable. Okay, just ignore that. So inside young generation we have add-in space, survivors S0 and S1. So you can think it like inside your young generation we have the one is add-on, then we have survivors S0 S1. All new objects start their life here. So like whenever you are creating any object, suppose I'm creating like the object which is your we were using the user, so let me call u1. This was your object. Very first it will go inside your young generation. Inside young generation it will go inside add-on. Okay, so when add-on fills up, minor gc occurs. So yeah, inside your young generation, or I would say in the add-on, when this will fill up, the minor gc will occur and it will check. What it does, it basically use your algorithms to like I can say the mark and sweep to like remove or like shift your memory objects which we need in the long time. Okay, so here you and then survivor spaces, object that survive their first garbage collection move here. So like suppose here we have u1, u2, u3, u4. We have a couple of objects here. So suppose after some time, like minor gc is like suppose it runs frequently, suppose after 10 seconds. So what it does, it basically checks, okay, now we do not have reference for u2 or u3. So what it does, it will just remove these and it will just send your like u1 and u4 here. This is not exactly like this, but here it uses some sort of like your counter variable, so it can maintain, because there is some threshold. I can write here threshold value correspond to each object. So and this like your the removal process is happening through your mark and sweep algorithm. We'll cover later in the video. We have mark and sweep, so we'll see there. So so why we use variable for the threshold? So suppose our threshold value is 3. So initially it was here, so your threshold value was 0. I can say the age or the counter value was 0. When it comes here it was 2, and here you can see object bounce between S0 and S1 during minor gc cycles, when your gc cycles run, like your minor gc. So when it moves from add-on to your S0, then from again it happens to S0 as well. Suppose it does not need your u4 here, and we also removed your this one, and now these are not here because these has been moved to the S0. Now we only have u1 here, and suppose meanwhile here we have added like your u5, u6, u7, a couple of another objects, and your u4 just u4 have moved to the u4 has been moved to your S1. And suppose here threshold value or the counter value has been reached to 3, or suppose you may u4 has moved back to here, and here its value reached to 3 threshold value. So what we'll do when the threshold value has been reached to 3, so where's pencil? Yeah, so what we will do, we will move this object into our old memory. Okay, so for long-lived objects that have survived multiple gc cycles, because your u4 has survived multiple your minor gc cycles, like it is using, like your program is using, your application is using this for a long time. So now we can move this into your old generation. Tenured space for long-lived objects that have survived multiple gc cycles in young generation. Here major garbage collection happens here, less frequent but more expensive. Okay, so so here what is major GC and minor GC. So minor GC you can just relate with like it's very frequently it's calling your GC. Sorry, very frequently it's calling your GC, but in your major GC you can suppose like a minor if every 10 seconds. So major you can say every 15 minutes or half an hour or might be 1 hour. It is like performing the GC cycles. Okay. So again, for your young generation, first time whenever you will create an object, it will go into your add-on, and then if after your minor GC, if it is surviving, then it will move to S0, your survivor 0, and after that it will just go along with your S0 and S1, never come back to your young generation or your add-on space. Cool. So string pool, we know the memory optimizer. So yeah, this is the example that I was like showing you, where here I created one example. No, what was there? So yeah, this was the example. So same example we have here. So S1 stored in string pool, S2 again literal, reuses S1 from string pool, S3 creates new object in heap. I told you the same. Cool. So next we have your meta space. So we created what's young done, old done, string pool done, meta space. Yeah, meta space. So like earlier before like Java 8 we were using your permanent generation, but after Java 8 we replaced with the meta space. Okay. So what it does, it basically stores I can say the class metadata storage. So like it stores your class metadata, static variables, const or method information, or the bytecode. So suppose you are creating const or class variables, your static variables or the class metadata you have, that all will reside in your meta space. Okay. Then heap memory example. So what is there stored in meta space? Oh yeah, this is like your I was talking about meta space, like class variables or static one stored in meta space. And we have main, all these objects are stored in heap memory. Like we use new for array list, new for person, and adding elements to the list. And numbers or I, each integer object goes to heap because numbers is my allocating memory inside heap, and then we are adding, it will create reference to those. And here we have a problem of memory leak. If you can point that out, just drop a comment. I know there is a memory leak. You have to tell me what is the memory leak here. Okay. So next we have garbage collection, the memory janitor. Garbage collection is Java's automatic memory management system. It identifies and removes. My iPad screen is just getting off because it's not charged. Let me check, do we have anything else for here? No, I don't think so we have anything else for the iPad. So I can just pause the next screen recording. And who is sending me this time? No, cool. So we can just keep our iPad aside. Okay. So garbage collection is Java's automatic memory management system. It identifies and removes objects that are no longer referenced, freeing up memory for new objects. Yeah, we know that. So popular garbage collection algorithms. So yeah, like earlier I was talking, or I can say, so earlier I was telling you like we just use your mark and sweep algorithm. So how it works, so yeah, you can see here the one is mark and sweep, mark face, basically inside mark face. So I need iPad screen. We have 9% charging in iPad, so we can use that. So where so yeah, here. So what it does in your mark space, suppose this is my memory, and suppose I have u1, u2, u3, u5, these all. Suppose I only need your u1 and u5 and I don't need u2 and u3. So inside your mark it will mark I need this, I need this, and in this sweep phase it will remove all unreachable objects. So like u2 is unreachable because it has marked, we don't need anymore. Same for u3, it has marked, we don't need anymore. So in this sweep phase it will remove these objects from the memory. So we'll get the memory, and then we have mark, sweep and compact. So what it does basically, so like so suppose this is our memory, and we have your u1, we have u2, we have u3, and we have u5. We are not using u1, we are not using your u5, and suppose there could be multiple as well. So again mark and sweep will happen. So what it will do, it will freed up these memory, and these memory are just called your fragments. So when we require this memory later in the future, but in your mark and sweep we cannot use. Suppose I need 12 KB memory, okay, but this is only 10 KB. I can say this is only the 2 KB, or the we can call it as 2 KB just, okay, or it could be any other number. Your 5 KB, this is your 10 KB. But what compact is does, it basically it basically compress. So your u2 will go here, u3 will go here, and all the fragments it will merge and just compact all the areas, freed up areas. So as you can see here, same as mark and sweep, but adds a compact phase, moves all leave objects together and eliminate fragmentation. All the leaved objects move together and just compress, combining all the fragmentation, so we can use. So now if we require 12 KB memory, we can definitely use this one, big block of memory. मुझे से याद आ रहा है ये ऑपरेटिंग सिस्टम में भी कहीं था, पढ़ा था ये, कुछ तो था ऐसा. Okay, so then we have our types of garbage collectors. One is your serial GC, and like this is serial GC is basically like when you are working with the single threaded applications where you have only one core, single core system, as it can see, small applications, single core systems, and like single threaded, low memory footprint. Then we have pedal GC. Nowadays pedal GC was there, so you were achieving your GC garbage collector, which is like efficiently freeing up the memory for you. Or these are like the your bash commands, so you can run these to like set whatever you want. And this is for your multi-core systems, because parallel multiple threads were running. So what it happened inside serial, because there is only one thread, whenever GC will run, it will stop or pause the main thread and GC will run and do the stuff. But inside your parallel GC, like multiple threads are running in parallel. So like one thread is just executing or performing their task, then we can parallelly run your GC task or GC thread. Cool. So multi-core systems, throughput focused applications, and multi-threaded, default in Java 8. So as I was saying, this was using, so yeah, this is default in your Java 8. Then we have G1, garbage first. So like this is like best for your large heap sizes, like low latency requirements. So it basically divide your heap into regions, like predictable pause times, and default in your 9 plus, Java 9 plus. Then we have ZGC and Shenunda. I don't know what is the pronunciation of this. Okay, so this is best for your ultra low latency applications, characteristic like your concurrent collectors with pause time under 10 ms. So like this was after your parallel, this was the like your JVM uses. So after parallel, your JVM was using your this G1 GC. Nowadays your G1 GC and GGC are being used inside your Java latest versions. So that's why it's as you can see, concurrent collectors with post time under 10 ms. So it helps to efficiently run the GCs, and these are the I can say your types of GCs. So nowadays these two we are using. So next we have memory related exceptions. What can go wrong? So stack overflow error, like cause stack memory is exhausted, usually infinite recursion. Haha. Hello infinite recursion. This will cause stack overflow error. Out of memory error, Java heap space. Heap memory is exhausted. List of string memory hog. While true, memory hog dot add new string memory leak. I told you there was memory leak in that program. You had to drop the comment. I don't know whether you have dropped, but I'll check if you have dropped. So here eventually goes out of memory error because this is a memory leak. You are just adding memory, and if you are just clearing up your memory hog, but again your memory references has been created. Okay, so out of memory error, meta space calls too many class loaded, rare in normal applications. Yeah, to be very honest, this is rare. So memory management best practices. So understanding object lifecycle. So create subject only when needed. Okay, set reference to null when done through. Set reference to null when done, though not always necessary. Yeah, not always necessary, but yeah, it's a good practice. Use object pools for expensive objects. Okay. Choose the right data structure. Use array list for indexed access, and use linked list for frequent insertion deletions. Yeah, of one very fast. Consider string builder for string concatenation. Yeah, because your string is immutable, so each time if we are adding or removing something from the string, so it is apparently creating the new string, as string is immutable. But for the these operations, you can use string builder, you can concat, you can delete caret, you can use string builder. Okay, so monitor memory uses. Okay, if you want to monitor how much memory is being used, what are the free memory I have right now, how much memory is freed in my system. So for the runtime class, you can call runtime dot get runtime. It will give you the instance of runtime, and then runtime dot total memory, free memory, used memory. You can check these all. Okay, so tune JVM parameters. So you can set your initial and maximum heap size here. Enable GC logging, you can enable this as well. And this is the quick reference memory types comparison. You can just take a look and to this table. And wrapping up, understanding Java memory management, or this you can just, I'm just leaving this up to you. You have to look into this quick reference table and wrapping up thing. And happy coding, and may your application never run out of memory. So yeah, that's all for this video. So yeah, one follow-up video will be there where we'll cover how C# garbage collector is different from Java, because C# is inspired by your Java. So we'll see there in that in the next video. So that's all for this video. If you found this video helpful or useful, so don't forget to like, subscribe and share. I'll see you in the next video. Till then, keep learning, keep growing. Bye bye.